Hi, in this video we'll go deeper into the creation of neural networks with PyTorch. We'll create a multi-layer perceptron for regression and use it to predict the price of a classic car based on its image. So our learning goals are to implement a fully connected network in PyTorch with the linear and sequential syntax, explore the necessary agreements between processing units and input size, understand the motivations for image input resizing, code input units, hidden layers, and output units, and examine the representation of weights, gradients, and loss in PyTorch. So this slide demonstrates a basic neural network architecture with three key components. We're going to have an input layer, a hidden layer, and an output layer. We have 3 nodes on the input layer, 4 nodes with a ReLU activation in the hidden layer, and 1 output layer that is going to give us a single value for the prediction. This is not the network that we're going to be using to predict the price of a car, simply because this one could only take 3 input features. This could be only 3 different values. This will have to be an image with only 3 pixels, or a tabular dataset that has only 3 columns. This is just a minimal example for us to explore this connection between input units, hidden layers, and output units. We see that nn.linear creates fully connected layers. The first layer transforms 3 to 4 features. The second layer transforms 4 to 1 feature. And ReLU adds a non-linearity between the layers. This is very important because if we don't add a non-linearity between the layers, then we're wasting the computation that we do when we do the multiplication of features times weights. And let's think about the model flow. We have sequential being used to combine the layers in order, and the forward pass processes input data. The loss function evaluates the prediction quality, and this is what we're going to be using to test how good our predictions are and also to update the model. The diagram matches the code structure. Note how each connection in the diagram represents a weight in the linear layers. So think about this minimal example as something that we're going to be exploring as a template for the next things that we're going to be looking at. We're going to be using a network that has more units in the input layer to predict the price of the car, but it's basically going to be the same structure overall. So let's inspect what we have in NN-linear. This slide examines the internals of this layer. We have a linear transformation from 4 input features to 1 output. This includes a bias term for added flexibility. This value is added to the dot product of the weights times the feature, and is also a learnable parameter. The layer contains as learnable parameters both the weights and the bias term. We're going to have as many bias terms as we have output units. So if we have 1 output unit, we're going to have 1 bias term. Take a look at the shape. The weight matrix shape is 1, 4. 1 output feature and 4 input features. The bias vector has a shape of 1, matching the output features, and the right side equation shows the matrix multiplication operation. The axis of parameters is important for us to see what is what. What are the weights and what are the bias. Each parameter has a name and shape, and this is very useful for debugging and inspecting models. The forward operation is done on a batch of 5 samples with 4 features each. The layer transforms each sample in the batch, and the output shape will be 5:1. The equation shows how the inputs multiply with weights to produce outputs. So this slide compares the effect of training a regressor using the mean square error loss with and without bias terms. In the Colab notebook that you see linked on the slides, you will see these two training loss plots, one for the model that has a bias term and the one that doesn't have a bias term. The blue line shows the model with a bias term, and the orange line shows the model without bias. The mean square error loss would quantify the error in prediction, and we see that both models converge, but to different minimum values. In this case, the model with bias fits better the data that we have in the example. You see in the scatter plot to the right that the blue dots are the training data points. The red line is the model with bias, which is fitting the data better, and the green line is the model without bias, which is forced to go through the origin. If we don't have a bias term, then we're forcing the regression line to always go through the origin of y equals 0. This is the reason why including the bias term gives a bit more flexibility and power to the model. The line can be displaced up or down. When we take a look at the loss formula, we see that we're measuring the average square difference between the predictions and the true values. N represents a number of examples that we're using for the evaluation of the loss, and that we're squaring the distances. So this is penalizing the large errors more heavily than the absolute error loss that we saw on the previous slides. This is a very good example for seeing the impact of bias versus no bias. If we were to change the loss function, which is an exercise that I would recommend you to do in the Colab notebook, if you change the mean square error to the L1 loss, which is the loss that we used before, you're going to see that the behavior is different. There is no guarantee that using the bias term is always better for our problem. It's something that is context dependent. This is a hyperparameter. So we need to do these explorations in a practical way in our particular problems. So let's take a look at what we have here with NN sequential. In this slide, we're examining the structure of a neural network using PyTorch NN sequential class. Let's break down the key components. We see again that the input layer has 3 features, the hidden layer has 4 neurons, 4 processing units, and then we have an output processing unit with just 1 neuron for regression. The code demonstrates the layer construction in which we are chaining these layers together. We have 2 linear layers connected by a ReLU activation function, and just for simplicity, we said that both linear layers are going to have bias equal to false. The network produces a batch of 5 examples, each one with 3 features. The visualization on the right shows the complete layer connectivity. We have fully connected layers, meaning that everything in the input is connected to everything in the output, and we have a data flow from left to right. Notice how the dimensions change through the network. We have this input with 3 columns, 3 features, could be 3 different intensities in pixels, that then are going to become 4. We're going to be using this hidden layer to create some synthetic representation, some synthetic data that is going to allow us to solve our problem a bit easier than using the input data that we have. So some common student questions that I have heard is why do we use NN sequential? Well, it's a very convenient syntax that simplifies the layer composition. we will see that there is another more powerful way to define the architecture of neural networks, and that is to subclass NN model and define implementations for the forward pass. This is something that we're going to see in the lecture related to classification with multilayer perceptrons. Another common question is, why do we use the ReLU between layers? So, as I mentioned before, ReLU is something that introduces nonlinearity. If we don't add it, we waste the computation that we do when we multiply features times the weights. And why do we use these specific dimensions? Well, the dimensions from the input and the output are given by the problem. So if we were to have a data set in which we had 3 columns or 3 pixels in the image, we would use an input layer like this. And if we were to predict a single number, like a price, then we'll be using an output layer like this one with just 1 unit. But this is dependent on the problem. However, the hidden layer is a hyperparameter. The number of units that we have in the hidden layer and how many hidden layers do we have is something that is up for discussion. We need to try it on every particular data set that we are interested in solving with our neural network to find what is the optimal number of hidden units or what is the optimal number of hidden layers. So here we have a fully connected network that is also called a feed-forward network or a multi-layer perceptron. This thing has several names in the literature, and this slide illustrates how this perceptron, this multi-layer perceptron, is being used for a car price prediction task. Let me walk you through the key elements. We're going to have the context of a task. We're trying to predict the price of a classic Corvette. So we're going to have to consider every single pixel that we have in the image as an input feature. That's going to be our X matrix of features. We're going to have also the price of the car being used as a training point, so that we're going to make our training network memorize somehow the price of this car based on its visual features. And we're going to make it produce an output. What we see in the slide is the actual price, the target, is 83,999 euro. But the network's prediction is 71,811. So the absolute error is the difference between these two numbers. The input structure is an image with size 1920 times 1282 pixels with 3 color channels. If we are to have an image of this size and we want to feed it into the model, we're going to have to create an input unit for every single pixel that we have. This is going to be humongous. We're going to have a total amount of input features that is more than 7 million. This is too much. This is something that will not fit in the RAM of most GPUs, and we're gonna have to do some workaround. We're gonna see what is the pre-processing step that we need to do on the data in order to make an image such as this one being something that we can feed into our neural network. We see that in the input layer, we also need to feed the model with flattened image data. So we're going to have to squish this image into a single flat vector that we're going to be using as the input. That's something that is going to be part of the architecture. We're going to have a call to a flattening method that is going to squish this image into just one long vector. We see that the hidden layer contains P neurons, and we have an output layer that has a single neuron for the price prediction. All the layers are fully connected, meaning that everything in the input is affecting everything in the output. So one of the first things that we need to do in order to work with this image is to resize it. If we were to use it with its original dimensions, we will have something that has over 7 million parameters. We cannot have that. The model is gonna be huge and is most likely gonna be picking things that are very spurious, like features that really don't have a significant impact on the prediction. One thing that we do all the time, something that is crucial when we work with images, is resizing them to make them more manageable for neural networks. Here we see that the original image has this humongous size, and then we can resize it using these transformations from PyTorch. The resized image is going to have 2 to 4 times 2 to 4 pixels with 3 RGB channels. Why these particular dimensions? Well, 2 to 4 times 2 to 4 is a very common image size. It was popularized by an architecture called AlexNet that we're going to discuss later. And we're going to find many models pre-trained online that already work with this 2 to 4 times 2 to 4 pixels dimension. The transformation pipeline shown uses the functions that you see here composed one after the other. So first we call toImage to convert the input into a proper image format, putting the channels first, then the height, and then the width. Then we call resize to reduce the image dimensions uniformly. We say resize 2 to 4, 2 to 4 to call a bilinear interpolation algorithm that is going to make the image fit the 2 to 4 and 2 to 4 target size. You see that it's a bit distorted. The dimensions of the car have been twisted a bit, but this is okay. In most applications, this twisting of the features is gonna still capture very important features for us to do a good estimation of the price of the car. You're gonna see this when you train the model. So this resizing is something that is very important for us to reduce the parameters of the model. We have reduced with this resizing the number of parameters by about 98%. The original model with the full size of the image had over 7 million parameters. After resizing, it has about 150,000. So this is important for us to be efficient in the use of memory so that we can also train the model faster and also to prevent overfitting. We don't want to take features in our input that might be too noisy, things that would make us actually have a harder time in learning significant correlations between the input features, between how the car looks and its target price. It's also useful for us to standardize the input sizes. The 2 to 4 times 2 to 4 size is something that we're using again because of the prevalence of the AlexNet architecture, but it's not set in stone. In fact, if we're going to be using a model trained from scratch, it might be better to make the image even a bit smaller. And that's something that we do in the next slide. Look at what we're doing here. Here we're calling center crop to capture more of the object of interest. And this is another conversion that is also very popular. You'll see many pipelines in which people do center cropping of the object of interest in order to reduce the number of parameters even more. Here we are center cropping the image to a portion of 992 to 992 pixels. And we're also using 2D type, torch float, scale true to convert the float values to convert the unsigned integer 8 values to floating point by dividing by 255, like we saw on the previous videos. So this sequence is set. We see that first we resize the image to a size of 256 times 256, which is larger than our final target, and then we crop to size 192 times 192 on the center. This two-step approach helps preserve more detail in our region of interest. So a key benefit of center cropping is that it removes potentially distracting background elements. We don't want the model to pick too much of the background. We ensure that the object of interest fills more of the frame, and this also standardizes the aspect ratio to square dimensions. It's very useful for us when we do deep learning to have these square tensors. It's not a necessity, but it's very convenient. It actually simplifies a lot the definition of the training loops. This further reduces the number of parameters, this center crop, versus just a resizing that we did before. So let's discuss a bit about the weight update rule that we do with stochastic gradient descent. A weight in a neural network is usually written as W with a subscript ij. The first subscript I tells us which input neuron the connection comes from, and the second subscript j tells us which output neuron the connection goes to. For example, W with subscript 1, 2 means the connection from neuron 1 to neuron 2. W with subscript 3, 4 means the connection from neuron 3 to neuron 4. Think of it like a road network. The neurons are cities, and the weights are the roads connecting them. The subscripts tell you which cities this particular road connects. When we update the weights, what we're trying to do is to adjust the width of these roads. The weights, when we first create a neural network, are initially random. However, we use a systematic approach to adjust them during training. And this is this rule that we see in this equation. The weight update rule, shown in the equation, helps us optimize the connections. First, we calculate how much each weight contributes to the network's error using partial derivatives of the loss with respect to every single weight, and we adjust each weight in the opposite direction of its error contribution. If a weight increases the error, then we decrease it. If a weight decreases the error, then we increase the weight. The learning rate controls the size of these adjustments, like making gradual improvements on the roads rather than just rebuilding everything at once. If you look at the diagram, the red connection highlights one specific weight being updated, and the orange line shows how this weight affects the final output. During training, all weights are updated simultaneously using this rule, and this process repeats until the network finds optimal weights. The key insight is that instead of us doing like some random tweaks, we use calculus to make a smart decision about how to change each connection to reduce the overall loss. So this slide shows a network design for image-based prediction. So what are we going to be doing? We're going to be feeding the image into the model after flattening it. And after we flatten the image, we're going to define a number of input features that comes from the number of channels times the height times the width. And then we're going to be putting a nonlinear activation, which in our case is ReLU. And then we're going to have a final linear layer that is going to produce a single output value. This sequential container simplifies the definition of the network. We see what comes first and what comes after. And this is something that is going to allow us to turn raw pixels from the image into a price prediction. In this slide, we see how the gradient descent implementation could be done. This is not the most efficient or the smartest way to do this, but it's a straightforward implementation of the equation that we see here. We're going to be updating the weights by subtracting from their current value their learning rate times the derivative of the loss with respect to the weights. And this takes three inputs. You see that what we need here are the current values of the weights, the gradient, and the learning rate, which is a constant value. And this constant value is super important to tweak right. It's going to make a huge impact on whether our network is trained correctly or if it's not. So you can also take a look at this image that we see here to get an intuition about what the gradient is. The gradient, you can think about it as the slope of a terrain, and in its positive direction will give you which is the fastest way to go up the terrain, the slope. On its negative direction, it will give you the fastest way to go down. So this is why we have this negative sign in front of the learning rate and the gradient, because we want to go in the negative direction of the gradient. In this particular implementation that you can go through, you will see how the weights of the two linear layers are being updated with the computation of this full rule. In practice, we usually do not do this, specifying like the weights layer by layer. We usually train with an optimizer. PyTorch comes with several functions that wrap this process of the weight update rule, and the most simple way to do this is to just import SGD. SGD stands for stochastic gradient descent, and we can simply pass the parameters of the model and the learning rate. Then when we call step on the optimizer, we're going to be doing something analogous to these updates that we were seeing before. When we train with these optimizers, what we're doing is creating like this wrapper that is going to put together everything that we care about: the parameters, the learning rate, and the gradients. Even though we're not explicitly passing them, this is something that's going to be working under the hood. If you take a look at what would be the trajectory of a stochastic gradient descent, something that is important to keep in mind is that this size of the update of the step that we see here is the learning rate. So how big is every single step that we take in the direction that minimizes the loss is something that we're controlling with the learning rate. It's important to not overshoot and also to not undershoot this minimum value for the loss, which is the best configuration possible that we can find for our weights. In this minimal diagram, we have a network that will have only two weights. In practice, we're going to have networks that have thousands of weights or even millions of weights. When we train with the optimizer, notice that you're going to have this pairing between the update rule and what we're giving the optimizer. We give it the parameters, the weights of the model, we specify the learning rate, and then we compute backward when we call loss.backward. The optimization that we're doing here is guided by the L1 loss. L1 loss is just another name for the absolute error function. When we do it over a batch of images, we call this the mean absolute error, because we're going to be computing the average of the absolute error on all of the training samples that we have. So this final slide demonstrates how the learning rate has a critical impact on the training. When we have a learning rate that is too low, like what we see on the left, we take very small steps towards the minimum of the loss. this is safe, but it might be inefficient. And when we take steps that are too big, like what we see on the right, we might overshoot. We might not reach the minimum of the loss value. What we want is to take steps that are just right, that fit the minimum value of the loss function. There is no guarantee that we're going to be finding this. We need to do these explorations by hand. This is why the learning rate is something that we explore as a hyperparameter search optimization. We need to explore with different values of the learning rate in order to find which is the best fit. We're going to do this in the practical exercises, and we're also going to look later in the course in some smart strategies to do this hyperparameter search of the learning rate in a way that is optimal. So we discussed the building blocks of PyTorch. We saw how neural networks in PyTorch combine linear layers, nonlinear activation functions, and loss functions, and how we can wrap these things together using sequential models. The framework of PyTorch has very good integration with gradient computation using AutoGrad. We saw how this is incorporated into the use of the SGD optimizer. We saw also how to process the images through resizing and normalization to create manageable feature vectors. We did the resizing of the images using both the resize and the center crop, and we also did the scaling using the 2D type. This is something that is very determinant for the performance of the network, because we're going to have as many parameters as we have input pixels in our images. We also saw a bit about model training. We saw how training combines the forward pass, the loss computation, backpropagation, and the weight updates. The learning rate is something that controls the stability of the optimization that we do on the weights and the convergence speed of our model. We're done.
Oh, it was a really long video.
Yeah. I think that the course was originally planned to be like two weeks. I think